Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy: black hole jets, giant molecular cloud, and protoplanetary disks. Unveiling black hole jets. The study of relativistic jets originating from supermassive black holes is a crucial aspect of astrophysics, as these jets play a significant role in shaping their surrounding environments. An international team of researchers took a major step in this direction by utilizing multi-wavelength observations of active galactic nuclei to explore how black holes launch these powerful jets. 16 sources were observed with the Event Horizon Telescope during its first observational campaign in 2017, providing an unprecedented opportunity to study jets closer to the black holes than ever before. The Event Horizon Telescope, an array of globally distributed radio telescopes, achieves extreme angular resolution by combining signals from different locations, effectively forming a telescope the size of Earth. This level of detail allows scientists to investigate the mechanisms that accelerate and magnetize jets as they emerge from the immediate vicinity of supermassive black holes. The research team, led by scientists from the Max Planck Institute for Radio Astronomy in Bonn, Germany, and the Institute of Astrophysics of Andalusia in Granada, Spain, recently published their findings in the journal Astronomy and Astrophysics. To test how well the current theoretical models describe the evolution of jets in active galaxies, the researchers compared observations from the Event Horizon Telescope with past studies conducted using the Very Long Baseline Array and the Global Millimeter VLBI Array. These latter facilities operate on larger spatial scales, providing a more extensive view of the jet's development over time. This comparative approach allowed scientists to trace how the jets evolved from their origins near the black hole to vast distances, spanning multiple light-years into interstellar space. The results revealed an intriguing trend: the brightness temperature of the jets, which measures the intensity of radiation emitted from a given region, generally increases as the jet plasma moves farther away from the black hole. This finding challenges long-held assumptions about how these jets behave. Traditionally, it was believed that jets follow a conical structure, with plasma moving at a constant velocity while the strength of the magnetic field and the density of the jet plasma gradually decrease with distance from the black hole. However, the new observations suggest a more complex picture. Jets are often assumed to be smooth and conical, but the research indicates that this model may not accurately describe all cases. The internal structure of jets appears to be intricate, with some showing signs of acceleration. This could mean that either the plasma itself is gaining velocity or that an observational effect caused by a bending jet makes it appear as if it is moving faster than it actually is. In some cases, when a jet shifts direction and aligns more closely with Earth's line of sight, it can create the illusion of an increase in speed. By examining a sample of 16 active galactic nuclei instead of just individual sources, the researchers were able to minimize the influence of unique characteristics specific to any single jet. This broader approach provided a clearer picture of jet behavior, revealing that brightness tends to increase with distance from the black hole, a strong indication that acceleration is taking place. These findings suggest that the mechanisms behind jet evolution are more dynamic than previously thought. The importance of intermediate-scale observations in this study was highlighted by Eduardo Ros from the Max Planck Institute for Radio Astronomy, who also serves as the European scheduler of the Global Millimeter VLBI Array. The Global Millimeter VLBI Array, which operates at a wavelength of 3.5 millimeters, provides critical information that bridges the gap between the highest resolutions of the Event Horizon Telescope and the larger-scale views of the Very Long Baseline Array. This was particularly evident in observations of the M87 galaxy, which played a central role in the Event Horizon Telescope's first major discoveries. Active galactic nuclei, the luminous centers of certain galaxies, are powered by supermassive black holes, and some of these objects generate relativistic plasma jets that extend thousands of light years into intergalactic space. Understanding the physics behind these jets requires observations with extreme angular resolution, enabling astronomers to examine their origins in detail. The Event Horizon Telescope, operated by a global network of scientists, provides this capability. In 2017, alongside its groundbreaking observations of the Milky Way's Sagittarius A and M87's black hole, the telescope also observed several active galactic nuclei to further investigate the behavior of jets. To assess the reliability of existing models describing jet evolution, the researchers compared the Event Horizon Telescope's data with previous studies that had mapped the same sources on larger spatial scales. This approach enabled them to trace jet development from their launch points near the black hole to the vast distances they reach in interstellar space. The results indicated that as the jet plasma moves farther from the black hole, its radiation power per solid angle, known as brightness temperature, tends to increase. This discovery contradicts the standard model of jets, which assumes a conical geometry and a constant velocity for the plasma. Instead, the new observations suggest that some jets exhibit acceleration, a phenomenon that may be linked to the role of magnetic fields, changes in jet structure, or interactions with the surrounding environment. The exact nature of this acceleration remains an open question, requiring further studies to fully understand the underlying mechanisms. Future research will focus on refining models of jet acceleration, the flow of energy within jets, and the role of magnetic fields in shaping their dynamics. The ongoing expansion of the Event Horizon Telescope Array will play a crucial role in these efforts, providing even more detailed observations of these fascinating cosmic structures. Jan Roeder, who led the study, emphasized that additional investigations are needed to fully grasp the physics of jet formation and evolution. J. Anton Zensis, director of the Max Planck Institute for Radio Astronomy and a founding chair of the Event Horizon Telescope collaboration, highlighted the significance of these findings. The study demonstrates the importance of international partnerships, advanced observational techniques, and persistent scientific inquiry in advancing our understanding of the universe. With upcoming improvements in telescope technology and the next generation of observational networks, scientists will continue to explore the complexities of black hole jets, uncovering new insights into one of the most energetic and mysterious processes in astrophysics. Giant molecular cloud found in Milky Way. Astronomers using the Green Bank Telescope, GBT, have identified a massive new giant molecular cloud, GMC, within the Milky Way galaxy, expanding our understanding of the interstellar medium and star formation. This newly discovered cloud, named M4 7-0.8, extends nearly 200 light-years and holds an estimated mass of approximately 160,000 times that of the Sun. This finding provides valuable insight into the complex processes governing the flow of matter in our galaxy and the birth of stars. Giant molecular clouds are vast reservoirs of interstellar gas and dust, composed primarily of molecular hydrogen. These clouds are essential to the galactic ecosystem, serving as the primary sites for star formation. GMCs vary widely in size, typically spanning between 15 and 600 light-years, and represent the densest and coldest regions of the interstellar medium. Because they contain the raw material for star formation, studying their structure, movement, and composition is fundamental to understanding how galaxies evolve over time. The discovery of M4 7 to 0.8 is particularly significant because of its location within the Milky Way. It resides at the midpoint of a dust lane in the galactic bar, approximately 23,000 light-years from Earth. The dust lanes of the galactic bar play a crucial role in transporting material from the outer disk of the galaxy toward its center. As gas flows inward, it accumulates in dense, ring-like structures where star formation activity is intensified. The presence of a previously unknown GMC in this region suggests that the process of material accretion toward the galactic center is more complex than previously thought. Observations of M4 7 to 0.8 have revealed important structural characteristics that provide insight into its composition and activity. The cloud stretches roughly 195 light-years in galactic longitude and extends about 65 light-years in galactic latitude. It maintains a cold dust temperature of around 20 Kelvin, highlighting its relatively undisturbed state. This low temperature aligns with the typical properties of GMCs, as these clouds must remain cold to allow gravity to overcome thermal pressure, facilitating the collapse of gas into dense star-forming regions. One of the most striking aspects of M4 7 to 0.8 is its internal structure, which exhibits two primary components. The first, dubbed the nexus, corresponds to the region with the brightest carbon monoxide emissions. This suggests it may be the densest and most active part of the cloud, where gas and dust are accumulating in large quantities. The second feature, known as the filament, is an elongated, narrow structure extending from the nexus. This filamentary shape is a common trait among star-forming regions, as elongated gas streams can funnel material towards sites of future star birth. Further investigation of M4 7 to 0.8 uncovered evidence of ongoing or potential star formation. Two specific regions, named Knot B and Knot E, were identified as possible sites of early stellar development. Knot E, in particular, exhibits a cometary-like shape and dense structure, leading astronomers to hypothesize that it could be a free-floating evaporating gas globule. These types of structures form when intense radiation from nearby young stars erodes surrounding gas, sculpting the cloud into intricate forms. However, additional observations are necessary to confirm this possibility and to determine whether these knots will eventually give rise to new stars. The observations also revealed an intriguing shell-like structure within M4 7 to 0.8. This feature appears to have a brighter rim and ammonia emissions, with a central cavity suggesting an area where gas has been displaced. Such shell-like formations can arise from various astrophysical processes, including the expansion of shock waves from stellar winds or supernova explosions. If this structure is indeed a remnant of past energetic activity, it could provide clues about the history of the cloud and its role in the dynamic environment of the Milky Way's central regions. The detection of M4 7 to 0.8 not only enriches the current catalog of known GMCs but also enhances the broader understanding of how molecular clouds evolve and contribute to galactic structure. By analyzing the properties of this cloud, astronomers can refine existing models of interstellar matter flow and star formation within barred spiral galaxies like the Milky Way. Future studies will focus on further characterizing the physical and chemical conditions within M4. 7 to 0.8, as well as searching for additional signs of active star-forming regions. The discovery underscores the importance of advanced radio telescopes like the GBT in probing the unseen structures of our galaxy. These powerful instruments enable astronomers to detect and analyze cold molecular gas that would otherwise be invisible at optical wavelengths. As observational techniques continue to improve, new insights into the interstellar medium and the mechanisms that drive star formation will emerge, deepening our knowledge of the cosmic processes that shape galaxies across the universe. Small protoplanetary disks challenge previous theories. Many of the protoplanetary disks where new planets form are significantly smaller than previously believed. Using the Atacama Large Millimeter/Submillimeter Array, ALMA, scientists from the Leiden Observatory in the Netherlands examined 73 protoplanetary disks located in the Lupus star-forming region. Their observations revealed that a substantial number of young stars are surrounded by relatively modest disks of gas and dust, with some measuring as little as 1.2 astronomical units in size. This research, which has been accepted for publication in astronomy and astrophysics, provides an important connection between observed protoplanetary disks and the characteristics of exoplanets. Over the past decade, astronomers have used powerful radio telescopes like ALMA to capture images of hundreds of protoplanetary disks surrounding young stars. Many of these disks extend well beyond the orbit of Neptune when compared to the size of our solar system. Additionally, many of them display gaps where giant planets are thought to be forming. However, new research conducted by Ph.D. candidate Osmar M. Guerra Alvarado, postdoctoral researcher Mariana B. Sanchez, and assistant professor Nyenker van der Merel from the Leiden Observatory suggests that these large disks may not actually be representative of the typical protoplanetary disk. By utilizing ALMA, the researchers conducted observations of all the known protoplanetary disks surrounding young stars in the Lupus region, a star-forming area situated approximately 400 light-years from Earth in the southern constellation of Lupus. Their findings indicate that 2/3 of the 73 disks studied are relatively small, with an average radius of just 6 astronomical units, roughly equivalent to the orbit of Jupiter. The smallest disk identified in the study measured only 0.6 astronomical units in radius, making it even smaller than Earth's orbit around the Sun. These discoveries fundamentally change the existing understanding of what constitutes a typical protoplanetary disk. The brightest disks, which are the easiest to observe, tend to exhibit large-scale gaps, while compact disks without such substructures are far more common. Most of the small disks were found around low-mass stars, with masses ranging between 10% and 50% of the Sun's mass. This type of star is the most common in the universe. The observations also suggest that these compact disks may provide ideal conditions for the formation of super-Earths, since most of the dust in these systems is located close to the star, precisely where super-Earths are frequently found. Super-Earths are rocky planets similar to Earth, but with masses that can reach up to 10 times that of our planet. This could help explain why super-Earths are more commonly detected around low-mass stars. The findings also suggest that the solar system originated from a large protoplanetary disk that gave rise to massive gas planets like Jupiter and Saturn but did not produce any super-Earths. Given that super-Earths are thought to be the most prevalent type of planet in the universe, this makes the solar system somewhat unusual compared to the broader population of planetary systems. The study provides a crucial missing link between the observed characteristics of protoplanetary disks and the properties of known exoplanets. The fact that the majority of small disks do not exhibit large gaps suggests that most stars do not host giant planets. This aligns with exoplanet observations of mature stars, reinforcing the connection between disk populations and planetary systems. Prior high-resolution ALMA studies primarily focused on bright disks, which are often significantly larger. In contrast, smaller disks had generally been studied only in terms of their brightness, with their sizes remaining uncertain. Capturing high-resolution images of these fainter disks posed a challenge, and it was previously unclear whether ALMA would be capable of resolving them. For this research, scientists utilized ALMA observations taken in 2023 and 2024 with the highest possible resolution of 0.030 arcseconds. In addition, they incorporated archival data to compile the first-ever complete high-resolution survey of an entire star-forming region. The results demonstrate that previous assumptions about the typical size and structure of protoplanetary disks were incorrect. Until now, studies have been heavily biased toward the brightest and largest disks. By expanding the scope to include disks of all sizes, a more comprehensive and accurate understanding of the early stages of planet formation has finally emerged.